Hi, today we're going to be talking about chemical equilibrium. And this video is really just an introduction to some very basic concepts. We're going to start diving into mathematical equilibrium fairly soon. Basically, what I want you to think about here is to re-envision the way that you look at a chemical reaction. A lot of times the way that we write a balanced chemical equation is we put the reactants on one side, we put an arrow pointing towards the products, and then we put our products. And that implies that reactions are one-way streets in which basically all of the reactants at some speed or another end up as products. End of story. But the question I want you to consider right now is, can reactions be two-way streets? Can we have reactants turning into products and products turning into reactants? For the reaction that I have down at the bottom of these last two slides, hydrogen gas and oxygen gas turning into water, the question we need to ask is, can that go both ways? Can what we call the reverse reaction actually occur? Can we turn water into hydrogen gas and oxygen gas? Is it possible? And of course, also, will that reverse reaction happen in the real world? Now, it is possible, I will say that. People are trying to use this to create hydrogen gas for fuel cell cars. But if you take a water bottle and you sit there and watch it, do you see hydrogen gas and oxygen gas bubbling out of solution? I personally never have. So how is it that despite the fact that this reaction is possible, we don't see it happening? So this is the other question we have to address with equilibrium, is which reaction is more likely to happen? When I say the word equilibrium, in a normal conversation, most people think of something like this, of people balancing. And so sometimes I'll talk about, one person balancing as they walk along a wall. In this case, I have a cartoon of a seesaw with two people balancing on it. But just because people can balance does not tell us how they balance, right? In this particular cartoon, I have two people who are the same size. And so it's easy for them to balance. But what would happen if one of them was taller and heftier? Then in the configuration that we just showed, the seesaw would tip to one side, to the side of the heavier person. The only way to make those people balance would be to shift where the fulcrum of the seesaw is, so that it's more heavily weighted to one side than the other. Now, obviously we don't have seesaws when we're talking about chemical reactions, but here's what we do have. We do have things called enthalpy and entropy of reactions. So we have the whole thermodynamics of the situation. And that gives some reactions more energetic heft than others. So we may have to slide and find that perfect balance between products and reactants where we end up with more products or more reactants, depending on what the energetics of that reaction is. Now, we're not going to get into the energy of equilibrium yet. That's still a couple of weeks away. What we're going to talk about is how we gauge where that balance is. And then later we'll get into energetics. We can tie the definition of equilibrium into kinetics. Basically, that the rate of our forward reaction equals the rate of our reverse reaction. So yes, we're creating products from the reactants. We're also creating reactants from the products. But since those are being produced at the same rate, their concentrations do not change. And that is the key thing in understanding what equilibrium is that equilibrium is where the concentrations have stopped changing. So sometimes people get equilibrium and kinetics confused. Kinetics looks at concentrations and says, how fast do those concentrations change? So as the reactants turn into products or vice versa, how fast do those change? That's not an equilibrium calculation. An equilibrium problem begins where the concentrations have actually stopped changing. What are the concentrations of your products once they have stopped changing? That's what we're looking at when we're looking at equilibrium. Or another way you could put it is equilibrium asks what the concentrations will be when they stop changing. Kinetics talks about how fast will it take your system to get to those concentrations. So yes, chemical equilibrium is a balance, but that doesn't mean we're going to have equal amounts of one thing or another. Chemical equilibrium is about finding where that balance is between the forward reaction and the reverse reaction, the balance between what some people might call reactants and some people might call products, even though they can each make each other. So that is just an introduction. Now I want you to go on to the next video where we talk about equilibrium constants, and we'll start diving into how we measure equilibrium and determine whether something is at equilibrium.